says, use Euclid's algorithm to reduce the fraction. The numerator is 5,829. Denominator is 18,879. This is, sorry, page 143. So, if you were doing this, if you were asked to reduce this to lowest terms, simplest form, whatever phrase you use, then you need to find a common factor from the numerator and the denominator. And the best one to find is the greatest common factor. If you can find the greatest common factor and take them out, then you know what's the factors that are left will not have any more common factors, and you will be left in lowest terms. So this is an example where you might not be inclined to find time factorizations of these numbers because they're really big and it might take you a really long time. So we might want to take the GCF, GCE, whatever phrase you use, with Euclid's algorithm, okay? All right, so this is the context for when we use Euclid's algorithm. When we want to find the GCF, that's what it is. It's an algorithm that returns the GCF of two integers. And the algorithm, again, is a step-by-step procedure that eventually returns an answer. And we all know, or we saw yesterday, why it is guaranteed to return an answer. Because eventually, in this long chain of kind of smaller problems that we end up getting, eventually we're going to get one that is the GCF of some number with 0. And we know in every single case, the GCF of a number a and 0 is that number a. Now, the reason, I think your main question is, why does it work? This is why it works. If you're given two numbers, it doesn't matter what two numbers, you can always perform long division on them and use the quotient remainder theorem to write dividend equals quotient, or sorry, let's write it the way that I did the other day. Dividend equals divisor times quotient plus remainder. Right? This relationship works all the time with whatever two numbers you choose. Right? You divide the dividend by the divisor. The quotient is the number of times the divisor goes into the dividend. And the remainder is what's left over, right? And we use letters like A, K, Q, and R just to make things easier to talk about. And furthermore, we also know, by the way, that R, the remainder, has to be strictly less than the divisor. Right? That's what the quotient remainder theorem guarantees us. Right. So, the key fact and the key fundamental truth that makes Euclid's algorithm go is the following. When you can do this, and you can always do this, right? It turns out that the GCF of the dividend and the divisor is always identical to the GCF of that same divisor and the remainder you get upon division. And it was quite painful, but we did explain that yesterday. We illustrated it with a couple of numerical examples, and then we tried to explain it algebraically. But anyway, this is true. I mean, this is a fact. It is a theorem. It is something that can be proven. And why this is useful to us is that these problems, we say, are equivalent because they have exactly the same answer, right? They're equal. Okay. But why this is useful is because K is smaller than A. Right? Because A is the dividend in case. So whenever you get a GCF problem, you're never going to get a problem where the two numbers are the same. I mean, that's a very silly problem. The answer's obvious. So you're always going to get a problem where the two numbers are different. So you're always going to have a bigger and smaller. So you can always divide bigger by smaller. And then the bigger one becomes your A, and the smaller one becomes your K. Right? So we start with A and K. So like in our problem, 18,879 would be A. 5829 would be K. So this tells us that the GCF of 58, let me write it, correction, 18,879 and 5829 is identical to the GCF of that same divisor 5829. And I have no idea what the remainder is when one divides 18,879 by 5829. We can probably figure it out. 5829 probably goes in there, I'm guessing, 3 times. 1,392 is the remainder. Right? So look what we did. We took a problem where the numbers were, almost 20,000 and almost 6,000. And we reduced it to a problem that has exactly the same answer, where the numbers are almost 6,000 and a little more than 1,000. So what the algorithm does is it returns equivalent problems than one you started with that are successively easier. Easier meaning they involve smaller numbers. And after a finite number of steps, could be 2 more steps, could be 20 more steps, you're going to get another equivalent problem where you get the GCF of some number A with 0. Because this remainder is strictly less than the divisor, right? So this remainder here always gets strictly smaller. So it has to be a finite number of steps. There's only a finite number of numbers between 1392 and 0. So it's not going to take 1,392 steps. Theoretically it could, but it's not going to. But the whole point is, if you're writing a computer program, it's going to just do the same thing, do the same thing, do the same thing, and as soon as it gets to this line, it's going to return A as the answer. So again, that's why I really took so many pains to really explain this fact, is because what you said is absolutely what can happen with this situation and other situations in math too. You're told a procedure, but like you said, you're just writing out the procedure and you didn't really know why you're doing it, right? Or why it works. You're just told, oh, this works, it's pretty cool, it works. It works because of this fact. You take 2 numbers, divide one by the other, dividend equals divisor times quotient plus remainder. It's always true that the GCF of the dividend and the divisor is the same as the GCF of the divisor and the remainder. It's just true. So you can just keep repeating the process. 5829 and 1392, that's too big of a problem for us to do too. Well, Euclid's algorithm tells us this is equal to the GCF of the divisor, 1392, and then whatever the remainder is when you divide that this by this. So we're getting smaller, right? It's got probably like, it's almost 1,426, probably in the 300s or so. It's how much? 261? Yeah. Right? So look at, in 2 steps, we've gone from a problem that's 18,879 and 5829 to one that's just 1392 and 261, right? So I don't imagine it's taking that many more steps. 87 is the next one. Or yeah, the answer. Yeah, right. So maybe 2 more steps. Other questions either on this or certainly anything else? Did people get like the factorial problem and the how do you find the number of zeros at the end of 10 factorial? Or those are some of the more, the proof that if you take any 3 consecutive numbers and you add them together, that is always going to be divisible by 3. I gave you that one.
How many zeros?
Yeah. So factorial, the concept of factorial is really important if you ever teach, well, probably not at the elementary school level, but if you ever teach or consider like basic ideas of probability, factorial comes up naturally in those types of conversations. So, you've all probably seen on a calculator or a computer a button that has just an exclamation point. That refers to the factorial symbol. Factorial means whatever number you have, factorial, you just multiply that number times all of the integers between that number and 1. So 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And as you can see, factorials get very big very quick. You're multiplying a lot of numbers together. So I think one of the questions asked for just the prime factorization of 10 factorial. Well, that's not too tough. 10 is 2 times 5. 9 is 3 times 3. 8 is 2 times 2 times 2. 6 is 2 times 3. 4 is 2 times 2. And then you just have to kind of collect them all together. We have how many twos? 1, 2, 3, 4, 5, 6, 7, 8 twos. And threes?
4.
And fives? And sevens. Okay, that part relatively painless. Now, the next question is, how many zeros are at the end? So if you were to type this in your calculator, how many zeros would you see at the end of the number that this is? So obviously the intent is not to do that. The intent is to look at the prime factorization and figure that out. What do zeros on the end of a number correspond to? Think divisibility tests. So do you know, if you know that a number ends in 0, what do you know goes into it? Okay. Right, but, yeah, but, and if you know a number ends in 2 zeros, what do you know goes into it? You know a number ends in 3 zeros, what do you know goes into it? Okay. So doesn't the number of zeros on the end of a number correspond to the number of factors of 10 that the number has? So that's what you're looking for. If you're looking for the number of zeros on the end of a number, you're looking for the number of factors of 10 that divide into it. How many factors of 10 divide into this number? And the hint is 10 is 2 times 5, right? You're looking for pairs of 2s and 5s, because those give you 10. So how many are there? Yeah, there's only 2 5s, right? Plenty of 2s. We're always going to have more 2s than 5s, at least in a factorial situation. So yeah, this is a 10, and actually they're right next to each other, so that's a 10 as well. So there are 2 factors of 10 that go into 10 factorial. That means there are going to be 2 zeros on the end. Does that make sense?
Can you show that consecutive numbers in divisible by 3?
Yeah, absolutely. If you call the first number x, what's the second number?
X plus 1.
And what's the third number?
X plus 2.
So if you're adding any 3 consecutive numbers together, it looks like this, doesn't it? What's the sum equal to? 3x plus 3? What does it mean to be divisible by 3? True, but we're never going to know the digits of this number because we don't know what x is. But that's the test. Let's go back to the definition. A number is divisible by 3 if it is a multiple. Yep, the multiple of 3. So can you write this as 3 times something?
X plus 1. Yeah.
That's the definition. This is the definition of being divisible by 3. Equivalently a multiple of 3. And that's pretty much a proof. That's really all there is to it. That does. I mean, you might write out in words, let the first number be x, and the second number is x plus 1, and the third number is x plus 2, then the sum is 3x plus 3, which is equal to 3 times x plus 1, which is 3 times a number. So by definition, that's divisible by 3. Any others?
5.43b.
Oh, yeah. Counterexamples. Yeah, I'm glad you asked about this because counterexamples can be really useful in the classroom. When you have students that... Yeah, so a counterexample, this is kind of another little bit of logic. We have, if you notice these statements in number 3 on page 124, they are all what are called universally quantified statements. Not to get into a ton of logic, but when you use words like all or for every, if you're asserting the truth of something in all cases, the variables you're using are what are called universally quantified. So if I come up to you and I say, this is true all the time, you can prove me wrong by doing what? Finding one example where what I say is true is actually not true. That's what we mean by a counterexample. Your example that you find is a counterexample to my claim, right? So in part A, you have a student that claims all odds are prime, right? So what would you have to do to find a counterexample? Find an odd that's not prime, right? If I walk up to you and I say every single odd's prime, if you find one odd that's not prime, you prove me wrong. Lots to choose from, right? 25. 25 is odd, it's not prime. Right? Very common one in part B. A student claims, and now again, when someone is claiming that a plus b the quantity squared is equal to a squared plus b squared, what they are claiming is that equation is true for all a and b choices, right? Because if you claim an identity is something that is true all the time. So if you're claiming this is identity, you're claiming it's true all the time. Well, how do you prove this statement wrong? What's a counterexample here? Like what form would it take? That'll do it. 4 and 5. A counterexample in this case, again, remember, a counterexample is this. What was a counterexample here? It was an odd number that's not prime. Okay? What's a counterexample here? It's a choice of a and b for which this equation does not hold. And you'd be, if you just guessed 2 random numbers, you'd be really lucky if you actually found 2 numbers that actually worked. Okay? So 4 and 5, that's an example, right? Let a equal 4 and b equal 5. You compute the left-hand side and you compute the right-hand side, and you show that they are not equal to one another. A plus b, the quantity squared, is 4 plus 5, the quantity squared. Well, we do parentheses before we do exponents, right? So this is 9 squared, or 81. However, a squared plus b squared is 4 squared plus 5 squared is 16 plus 25, which is 41. That should end the discussion. It doesn't, unfortunately. It should end the discussion. So counterexamples are useful when, because it's not, you probably found out, it's not useful when a student thinks something's wrong just to say, you're wrong, this is right. So the more ways you have to kind of convince them that they're wrong, then you can move on. Once you've agreed, okay, we can't do it this way because it doesn't work in this case, then we can move on to talking about what's right. The last point I like because it teaches us the lesson that just because something holds, a pattern holds for a while, doesn't mean it always holds. So, Tiana conjectures, and that means she guesses, that the equation n squared plus n plus 11 always returns a prime number. And if you look at the first 5 values of n, she's right on the money, isn't she? Because 1 squared plus 1 plus 11 is 13, and that's prime. And 2 squared plus 2 plus 11 is 17, right? And that's prime. And 3 squared plus 3 plus 11 is what, 23? And that's prime. 4 squared plus 4 plus 11, 31. 5 squared plus 5 plus 11, 41. So we might be very convinced that she is onto something here, right? Because 5 examples, 5 winners. 6 squared plus 6 plus 11. 36 plus 6 is 42, plus 11 is 53. Is that prime? 7 squared plus 7 plus 11. 49, 56, 67. 67 prime? 8 squared plus 8 plus 11. 64, 72, 83. 83 is prime, right? Perfect from that space. 9 squared plus 9 plus 11. 101?
Yeah.
101's prime. 10 squared plus 10 plus 11. 121. It's 11 times 11, right? So it took a while, but we got there.
I actually shortcoded it. Because I looked at her equation and realized that if you put in 11, it would have to be a multiple of 11 because you're multiplying 11 times itself and then adding, which is just multiplication meaning adding over and over again, but she automatically made a flaw.
Very clever. Right? The number 11, very clearly, without going through the extra steps that I went through, is going to work. 11 squared plus 11 plus 11, you can factor an 11 out of that whole thing. It's 11 times something. We're done. Excellent. Again, good object lesson that patterns don't always hold. Others? Anything else on that? Okay, well again, if something comes up, wow, you guys have a knack of being right on the time, or maybe I'm good at picking the amount of time to devote to homework. But actually, before we move on to fractions, there was one exercise. Oh, okay. There's one exercise that I didn't give you that I think is pretty interesting. It's in the same section. Actually, it's one of the next problems in that section on page 124. And this type of exercise can, if you remember the conversation we had about how many prime numbers are there, infinitely many or finitely many, we can make a reasonable case for either answer. But this type of exercise that is done in number 5 on page 124 can be really good evidence, actually, that there are only finitely many primes, even though we already proved there's infinitely many. Because what I can do in number 5, amazingly enough, is I can construct a sequence of numbers of any length that you want. So a sequence of composite numbers of any length. What that means is I can take a sequence I can write down 1 billion numbers in a row, none of which are prime. And I can prove it really easily that all the numbers in my sequence are not prime. And if 1 billion is not good enough for you, I could write a sequence of 10 billion numbers in a row, none of them are prime. Meaning, in the number line, there is a 100-mile gap between two prime numbers. Does everyone kind of grasp the implication of that? So if you think of a number line and each number is separated by an inch, I guess we'd have to compute that. That would be a good exercise. Each number is separated by an inch, and I wrote down 1 billion numbers in a row that weren't prime. The gap between two primes would be, I don't know, but it would be pretty simple. And we use factorial and this idea of factoring to accomplish it. So they start off with a pretty kind of benign type question: 6 factorial plus 2, 6 factorial plus 3, 6 factorial plus 4. They just have you kind of consider these numbers. And these numbers are small enough that we can, they're 6 factorial is 720. So these numbers are small enough that we could just easily show, not even using factorial or factoring for that matter, that none of these numbers are prime. Obviously, if you're taking any factorial is going to be an even number, isn't it? Except for one factorial, because every factorial is going to contain what is a factor, right? So every factorial is going to be 2 times something, so it's going to be even. But that's not, so I don't, and I'll give this problem to my students, and they'll say, oh, this is 722, so this is by 2, this is 723, and this is by 3. That's not what I want. So what I want is, or what I'm looking for is, can you come up with a kind of a general procedure that will work when I change that number 6, okay? These numbers are sequential, right? Because I started with this one, and I just added 1 to it, and added 1 to it, and added 1 to it, and added 1 to it. So this is 5 consecutive numbers, right? So I claim to you that none of these numbers are prime. And we can see this rather easily if we just write out what 6 factorial actually means. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1 plus 2. Can you tell me automatically a number that goes into 6 factorial plus 2? Thinking distributed property in reverse. Is there a common factor do you see? If 2 goes into both of those, right? Divisibility lemma again. If 2 goes in here and 2 goes in here, then 2 goes in here, right? If 2 goes in here, it's not prime. Is everyone okay with that? What do you suppose the factor to the next one's going to be? You are correct. If 3 goes in here, and 3 goes in here, then 3 goes in here. We could show it by factoring out the 3 and using the distributed property, but we could easily use the divisibility lemma too. If 3 is a factor of this number, it's not prime. And 4 is a factor of this number by the same trick, so it's not prime. Trick technically. And 5 is a factor of this, so it's not prime. And 6 is a factor of this, so it's not prime, right? Now, can I do this with 6 factorial plus 7? No, because 7 is not a factor of 6 factorial. So I'll stop. But what I have written down is a sequence of 5 numbers, consecutive, none of which are prime, right? Because 2 goes in here, 3 goes in here, 4 goes in here, 5 goes in here, 6 goes in here.